Turning to the top of page 11. Now, this is a topic that a lot of students find confusing, so let's focus on this one. And that is, we've spoken about the types of bonds, ionic and covalent, types of covalent bonds, polar and nonpolar. Now let's talk about the types of molecules. And there are two types of molecules: dipoles, also known as polar molecules, and non-dipoles, also known as nonpolar molecules. And that's where the confusion lies, because we use this word polar to refer to molecules and to refer to bonds. So, let's see if we can break this down. The easiest way to think of it is the molecules that have symmetrical shapes, and I have the shapes here depicted for you. CH4, symmetrical. The CO2, symmetrical, meaning balanced, evenly distributed shapes. The Hakelbriefs, for sure. Molecules with symmetrical shapes have an even distribution of their charges, and because of that, they're called nonpolar molecules. On the other hand, the molecules that are asymmetrical in shapes will have an uneven distribution of charge, and so water, NH3, and HCl would be polar molecules, also known as dipoles. Okay, maybe to illustrate this, a little human video here. I have the classic ball and stick model of CH4. I'm sure you've seen this many a time. All right, just look how symmetrical this molecule is. No matter which way you look at it, it's the same thing. All right, another way to illustrate this is, let's see what CH4 does. It landed on its feet here. It lands on its feet each time, like a cat. Maybe you could give it a little break dance here to help you with that. There it is, it lands on its feet. You can't see that. CH4, I think of CH4 like a break dancer. Very, very symmetrical. One more time, huh? There you go. How balanced. Anyway, that might help you to remember that. Let's break this down a little bit further, and again emphasizing the water's angular, the NH3 is pyramidal, the HCl is linear, and a lot of times students have problems with that. They say, well, how is it that the HCl, being linear, and the Hakelbriefs, which are also linear, since any molecule consisting of two atoms has to be linear in a straight line, how could it be that one is nonpolar and the other one is polar? Well, again, just look at this. When it comes to the Hakelbriefs, you have mirror images here. You have the same thing on both sides. And in the case of the HCl, very different. All right. Towards the bottom of this page, you'll see another way to analyze this. Let me get a piece of paper towel to break this down for you. Let's take a closer look at this. Again, H2O has polar bonds. And why is that? Well, that's due to the different electronegativities. When we talk about bonds, you have to consider electronegativities. Remember, hydrogen's 2.1, oxygen is 3.5, and hydrogen 2.1. So what we're saying is, in these bonds, the electrons are shifting towards the oxygen. The oxygen would therefore acquire partial negative charge. And the hydrogen's the opposite, partial positive. So this molecule, you see, because electrons are shifting this way, clearly has a negative side and a positive side to it because of its asymmetrical shape. So that asymmetrical shape leads to a polar or dipole molecule. Another way to depict that is to draw any molecule that is a polar molecule as an oval with a negative pole and a positive pole. A negative side and a positive side to it. Hence the word dipole, which means two poles. I mean, in analogy, you think of the Earth with its equator having a north pole and a south pole. The Earth is a dipole, but in that case, in this case, it's with respect to magnetism. Let's look at CO2. CO2 also has polar bonds. Why is that? Due to the difference in electronegativities. 3.5, 2.6, 3.5. And because of that, the electrons are shifting towards the oxygens, which are partially negative. The carbon being partially positive. In this case here, because there's a symmetrical shape, that symmetrical shape leads to a non-polar molecule. An asymmetrical shape leads to a polar molecule, but a symmetrical shape, a non-polar molecule, because what you can think of this as a tug of war. The electrons in this bond are being pulled this way, and in that bond the opposite way, but as a result, the electrons, in the end, stay in the middle. Because you can always think of a bond as a tug of war. Or, another way of saying it is, the center of positive charge, the place in this molecule where positive charge is focused, is the carbon. And the center of these two negatives is also the carbon. So what we're saying is, in this molecule, the centers of positive and negative are in the center, and so they cancel out. While in this molecule, in terms of centers of charge, the center of negative charge is the oxygen. The center of these hydrogens is somewhere here, separate from the oxygen. So since the centers of charge here are in two different places, this molecule is a dipole, and this molecule is a non-dipole. Now that I've confused you maybe even more, here's the main point. When they ask you if a molecule is polar or non-polar, consider the shape. Non-polar molecules have symmetrical shapes. Polar molecules have asymmetrical shapes. That's the best I could do for you. Now let's move down and consider the attractions between molecules. In other words, how does one molecule stick onto another? And we call this topic intermolecular forces of attraction. Inter, in this case, meaning between. We mentioned this in the first unit when we spoke about boiling points. So we're talking about the forces between molecules. But in the first unit, I didn't give you any details as to what those forces were, other than saying that liquids that had stronger intermolecular attractions had higher boiling points. Hence, the IMAs, or intermolecular forces of attraction, affect or determine vapor pressure, intensity of a liquid to evaporate, boiling point, solubility, and other properties like that. As far as IMAs are concerned, there are 4 IMAs that you should know about, and these 2 in particular. Dipole-dipole attraction is the attraction that occurs between dipoles. So, again, dipole or polar molecule, anything on the left side of your top 6 will give you this. Let's pick HCl. In the case of HCl, one HCl is attracted to another HCl molecule because the poles are oppositely charged. So it's all electrical in nature, as always. Opposites attract, but in this case it's oppositely charged poles attract. The attraction is called the dipole-dipole attraction. It's the attraction between polar molecules. Now the same kind of attraction exists also between water molecules, since water molecules are polar also. But in the case of water molecules, it's a much stronger dipole-dipole attraction, a super dipole-dipole attraction. The reason for that is 2 reasons. The oxygen in this case, if you recall, is one of the top 4 electronegativities. In fact, it's second to fluorine, so the oxygen is really pulling strongly on these electrons. And because of that, the oxygen has a negative charge, a partial negative charge, that is much greater than in the other instances. So, in the case of oxygen, with hydrogen, all right, because the electrons are shifting so much towards the oxygen, the magnitude, the amount of negative charge on the oxygen is much greater than in ordinary molecules, and therefore the amount of positive charge on the hydrogen is also much greater. So you can think of this as a dipole-dipole, but it's a dipole-dipole with a fat negative and a fat positive. greater magnitude of charge. And since there's a greater magnitude of charge, there's going to be a stronger attraction, intermolecular attraction, between the molecules. And so if I'm using dashed lines to represent that attraction here, in this case, you're going to have more dashed lines. The attraction is so strong, in this case, that we give it a different name. We call it hydrogen bonding. So hydrogen bonding is the attraction of a hydrogen atom in a molecule for fluorine, oxygen, or nitrogen in another molecule. All right? And this occurs only when hydrogen is directly bonded to fluorine, oxygen, or nitrogen. The reason for that is like oxygen, the fluorine and the nitrogen have high electronegativities and small atomic radii. So you see, the magnitude of that charge is not only due to the electronegativity, it's due to the fact that these partial charges are involve small atoms. So there's a greater density of charge, if you will. All right, that might sound just too complicated. So how about we remember it this way? Hydrogen likes to have fun. It's a silly way to remember that anytime you have hydrogen directly bonded to fluorine, oxygen, or nitrogen, then hydrogen bonding has to exist between its molecules. Let me draw that for you in some other examples. The students really find this confusing. So I have some space at the bottom of this page. Let me show you the classic examples. Again, hydrogen bonding is the strongest intermolecular attraction. Because that attraction is so strong, we get abnormally high boiling points. So, then between water molecules, you'll have hydrogen bonding. Between HF molecules, you'll have hydrogen bonding. Notice the hydrogen bonding is between the molecules, not within the molecules. What holds the hydrogen to the fluorine within the molecule is a covalent bond. It happens to be a polar covalent bond. Then we should also mention NH3. So you have one NH3 and another NH3, again, hydrogen bonding, leading to abnormally high boiling points. And that's typically the question they ask about hydrogen bonding. Okay, if you come to the bottom of this page, you got one more page to go in bonding. You take a rest, try to take in what I just said once again, or go straight to it.